In this next section, we'll talk about zeros of a polynomial function and their multiplicities. And a fun fact, you can actually spell zeros like this or like that. So I kind of spelled it both ways, not intentionally, but just FYI, they're actually both correct. All right, so zeros of a polynomial function, we'll go there first. These are the x values, which make your function value equal to 0. So for something like this, f of x equals negative x minus 1 squared times x minus 4. We can set each factor equal to 0. So setting x minus 1 equal to 0, we solve that and we would get x equals 1. So that would be our first 0 of the function. Then we could set that second factor, x minus 4 equal to 0, and get x equals 4. So these are our two zeros of the function. So it sounds a little weird. The zeros of the function are 1 and 4, but that's one name for this. Graphically, by the way, the graph is down here. So these are going to be our x-intercepts on our function graphically, right? All right, the multiplicity. So if we want to find the multiplicity of each zero, this comes from the exponent. So remember we took the factor x minus 1 and we set it equal to 0 to get that first 0 of x equals 1. The exponent of that factor is 2. So x equals 1 has a multiplicity of 2. For my 0, x equals 4, that came from this factor, which has an understood exponent of 1. The multiplicity of x equals 4 is 1. Okay, so talking about multiplicities, why do we even care about these multiplicities? So down here in this box, it says if r is a 0 of even multiplicity, like this guy is, the graph touches the x-axis at r but does not cross the x-axis. The graph behaves like a parabola. Okay, so let's look at our x equals 1. This has an even multiplicity. Even multiplicity of 2. And you can see that the graph right there is behaving like a parabola, behaves like a parabola, which means it touches the x-axis but doesn't cross. Now if we look at our x-intercept of 4, which has an odd multiplicity of 1, so odd multiplicity of 1. Down here in the box it says if r is a 0 of odd multiplicity, the graph crosses the x-axis at r. The graph behaves like a line at this point. And you can see that here our graph is behaving like a line in that it crosses the x-axis. Okay, parabolic behavior versus crossing the x-axis, behaving like a line. Okay, and by the way, bonus points down here, the end behavior. If we were to look for that leading term, we'd have f of x or y. That would equal negative, and then we'd have an x squared from that first set of parentheses. And then we just have x. So multiplying this out, negative x cubed, So that's going to look something like this for the end behavior. So it's going to rise to the left and fall to the right. We can see that on our actual sketch, rises to the left, falls to the right, and then just confirming based on that leading term, we got the same results. Okay, cool. So let's take a look at this graph on the right and its equation. F of x equals x plus 3 times x minus 1 times x minus 3. So setting each of these factors equal to 0, if I set x plus 3 equal to 0, that gives me my first 0 of x equals negative 3. Multiplicity of 1. Set x minus 1 equal to 0, gives me x equals 1. Multiplicity of 1 from the exponent of that factor. Setting x minus 3 equal to 0 gives me x equals 3 and multiplicity of 1. So all three of these have multiplicity of 1. Those are all odd multiplicities. And you can see at the x-intercepts of -3, 1, and +3, these are behaving like a parabola. So they all behave like a parabola. Oops, sorry. I don't know why I said parabola. They all behave like a line. My bad. Behave like a line, meaning they cross through that x-axis. You can see they cross, boom, cross, boom, cross, boom. Even, like y equals x squared, that's our basic parabola. When we have odd, behaves like a line crosses through the x-axis. And end behavior, if you just look, you can see it appears like it's falling to the left and rising to the right. But let's just confirm that by pretending to distribute out all of this. So we've got x times x times x. This is going to behave like our y equals x cubed function, which falls to the left and rises to the right. Okay, so those are zeros and multiplicities. And by the way, we talked about zeros and then we talked about x-intercepts, and they're pretty much the same thing. Just a little FYI, when you're finding zeros of a function, there could be complex solutions, complex values of x that make your function equal to 0. So you could have an imaginary unit I as a 0. X-intercepts always have to be real numbers, so just a small distinction. But for the most part, we'll use them interchangeably because I don't think that you're running into any complex zeros in this section. But just an FYI, they're pretty much interchangeable except for that distinction. Okay, so determine without graphing the x-intercepts, meaning the zeros, and their multiplicities. All right, so function A, f of x equals x minus 5 squared times x plus 2 times x minus 4 squared. So setting x minus 5 equal to 0 would give me x equals 5 as the 0, or as an ordered pair, 5, 0, right? That would be the ordered pair x-intercept. If x plus 2 equals 0, then I'm going to get x equals -2, oops, or the ordered pair -2, 0. And x minus 4, if I set that equal to 0, I'm going to get x equals 4, written as an ordered pair 4, 0. So these were the x-intercepts that will appear on the graph from x equals 5, x equals -2, and x equals 4. For their multiplicities, for x equals 5, it has an exponent of 2. So the multiplicity is 2, which of course is an even number. For -2, the multiplicity is 1, which is an odd number. And for x equals 4, the multiplicity is 2 from the exponent, which is an even number. Okay, so if we take a look at this function, at the graph of this function, at our 0 of x equals 5, it has an even multiplicity, meaning it should behave like a parabola. So it's going to touch the x-axis but not cross through. At x equals -2, we have an odd multiplicity. So it should behave like a line in that it should cross the x-axis. And then at x equals 4, we have even multiplicity. So again, it should behave like a parabola, meaning it touches the x-axis there. Okay, and let's just take a look at this and see if we can get a nice view on our graph. Sometimes it's a little hard with these polynomials. X minus 5 squared times x, oops, sorry, well, that was weird. Okay, here we go. X minus 5 squared times x plus 2, close parentheses, and then times x minus 4 squared. Take a look at that. So using the trace function, if we go to, we'll start in negative territory first. So there's x equals -2, y equals 0. We can see that our graph is behaving like a line. It's crossing through the x-axis there. And then if we go over to x equals 4, or y equals 0, we can see that we do have that parabolic behavior. It's just touching the x-axis. And same thing for x equals 5, behaves like a parabola, just touching the x-axis. Okay. All right, so let's take a look at our next function. F of x equals x cubed plus 4x squared minus 9x plus minus 36. So we want to get this in factored form. So if you don't have it factored, go ahead and factor it as a first step. So we can factor out our GCF x squared, and this gives me x squared times x plus 4. For our second terms, we're doing factoring by grouping because we have 4 terms. If I factor out my GCF of -9, that leaves me with x plus 4 in parentheses. So at this point, I have x squared minus 9 times x plus 4. And then x squared minus 9, I can break apart using difference of squares. So x plus 3 times x minus 3 times x plus 4. So there's my factored form of my function. So again, the x-intercept, setting each of those factors equal to 0. X equals -3, x equals +3, and x equals -4. All of them have a multiplicity of 1 because the exponent on all of those factors would be 1. So they all have a multiplicity of 1, which is odd, odd, odd. So across the board, these guys should behave like a line, and they should cross the x-axis. So true for all 3.